lecture as usual and topics. You can take a look. Well, and again, this equation which was just recently in Blumenstock, this is the Dennis company's equation. And then he would have just constant parameters, so that you know to make one 0 and so on. Just I wanted to illustrate that how to calculate invariant solutions. That's the reason. And some of them, like I already told about this, I think maybe, or it was another, it was a not lecture, but presentation for the conference. This stationary solution is also interesting. You know how to obtain it? Just let me return. So, if n, just it's for students, not for teachers. If n does not depend on that, t becomes 0. And then it means that after integrating with respect to x, since it depends on t, you obtain that it's constant. What is inside this expression is constant, and multiplying that constant by x2 or dividing by x squared, you obtain here is the constant. This one is constant. And different particular solutions, physically important solutions, they are taken from physics. They were obtained by, not by using, of course, using company's equation, they were obtained from physics, by using statistical physics. Very interesting and complicated topic. So, and let me just okay, maybe illustrate some of the invariant solutions anyhow. No, that case is not interesting. Sometimes we obtain complicated ordinary differential equations. For example, if you take this generator, this generator, oops, again it is, yeah, let me just let me just find that equation what we need. Equation 3, equation 3. So equation 3 is here because we cancel that term which gives the higher order derivative nx, and equation here is the equation. And if we take, just I wanted to illustrate this complicated case. The equation 3 admits the operator x3, and you calculate its invariance. One invariant is lambda equals t times x from here, and another one is n, of course, because it does not differentiate, it does not have any differentiation with respect to n. So we have two invariants, and we take one invariant, which denoted by lambda, which does not involve the dependent variable n. Of course, it's not always possible, but in this case it's possible. This is a simple case. We take as new independent variable and phi as new dependent variable. And then equate this new dependent variable, this again n, to any function of lambda. Lambda is given here. And this expression is substituted in equation 3, which was I showed already. An ordinary differential equation of the first order. After substituting, it becomes like this. And you can integrate this equation. because the variables are separating. You solve that equation and obtain the solution in this form. So,
this is the one-term equation. One-term equation, just a non-linear term.
Sorry?
It's just a one-term. It's a
Yes.
first-order equation, not a second-order equation.
Yes, first order, yes. Now, if you have in different other situations, again, we have invariance, and substituting in this case, obtain that equation with another situation, this one. When I just take out the term n, and you obtain second order equation which I cannot solve. So, invariant solution, when you have not always possible to integrate them, the second order equation, ordinary. So, I cannot solve myself this. Maybe somebody can. So anyhow, other solution. This is another model now. So I finished with the comprehensive equation because we already had a new solution from George Stokes. So it's very interesting. Now, I would like to show several models where solutions can be interesting from a physical point of view. The model is like that. The history was, I was in Georgia, visiting Georgia Tech and visited Athens, the University of Georgia, and I was introduced to Dean, who was working on pollution problems, pollution of the groundwater because of irrigation systems. And they told that it's a big problem, and the government gave a lot of money for that, and they made a research group which consists of two parts. One part is theoretical part, where he was the leader, and another part engineering part, the basic, the main part, more people, more money. And first they had to give recommendations of constructions of improving the system, the irrigation systems for engineers, so that in order to minimize the costs of constructions. And he told that so far we have considered several models, and one of them is this one, which seems to them quite physically appropriate to the problem, to their concrete problem, because all systems are different, so for their situation it was appropriate, and they wanted to investigate solutions of this equation. So I will not, with physical science, the main thing for the water, underground water, and they want to understand what goes on. So all these functions are, they have some engineering sense. Like it doesn't matter for me, just equation. Well, this is the beauty of mathematics. When you come to a concrete thing, you don't need to deal with all these materials and so on, just to see differential equations. And that's why it's very important if you have a research, you have to make research. Should be a research group containing several people and mathematicians, and one possibility also there. So, and then he told, numerically we could not solve, we could not say anything. It has many difficulties. So, and he told, by your methods, can you find any solutions? Because except very trivial solution, we don't see anything. So that time, of course, I could not see just immediately, it's complicated. When I returned home to Moscow, I think, that time I wrote there, and I invited Kovalyov, and Gazizov, and Laikov, so 4 of us were calculating, and I don't remember Laikov was also there or not, but anyhow, we found that, first of all, we made a group classification. What it means? It's using symmetry properties, determining equations. You have to find, first of all, you find trivial, the symmetry which is admitted for any unknown function C, K, and S. There are three functions of one variable. In this case, independent variable is psi, and independent variable of T, X, and Z. So T is time. So group classification means find those functions C, K, and S such that the equation with these coefficients has more symmetries than the equation without three coefficients. So that should not be process. Well, when we did this work, it was terrible work. I think maybe at that time it was only by hand. I think nobody could at that time use computer algebra. Maybe today it's easier. We found 29 types. When the group becomes larger, or algebraic algebra becomes larger by 1, 2, and so on operators. And then investigate some invariant solution without any technical applications. So we found for one of them, which is based on like two fixed symmetries, and the solution looks like it was invariant solution. And but of course, without the group property, it is just you cannot even see in your dream this kind of solution. It's very complicated, but the picture of the solution is very nice and gives some interesting ideas. Where more water, where less water. And I was joking that the paper it was made in, I think, in Florida, and it was used originally created for investigating some kind of tomato problem, how to grow tomatoes and so on. And I was joking to that tell to your mother that how you should produce tomatoes, in which places she put seeds and so on, in order to have more tomatoes. So this is one of the practical problems.
Excuse me.
And another problem, which I saw just some 2-3 years ago, it came from metallurgical industry. Just because I'm trying to show you some industrial engineering problems which can be formulated by differential equations. So the idea there was when it's about liquid metal systems. It's metal casting, for example, iron or aluminium or anything else. So it is it's like a liquid in the beginning, very hot. Then we put it down, and it flows like a liquid, but metal liquid, and collect somewhere to forms and so on. It becomes a hard metal. In this process, unfortunately for industry, that when the liquid metal becomes hard metal, there appear bubbles inside. And those bubbles make the metal not appropriate for industry. It's not strong enough and so on. Many cracks can appear afterwards and so on. That's why they try to eliminate those bubbles. First they were just doing that by shaping, mechanical shaping. And of course, because of their pressing, bubbles are going out, but not all of them. A lot of them stay in the metal. It doesn't matter how quick the shaping is, the vibration. And then it was found that let's use for that purpose a magnetic field, which is oscillating quickly. And then choosing also how strong it should be, that field and so on. But then we had another problem. Of course, it helped very much. But then we had the problem of what's so-called skin effect. Because magnetic field cannot exist just by itself. It creates some electrical current. So it is called skin effect. And this electricity also spoils the process. So how to improve that thing is something they wanted to understand. And then one model was suggested by a Moffat from London, from a very famous laboratory of mathematics. By the way, and Newton worked there in that laboratory. And then Dirac, one of the great mathematicians, is the head of this department sometime. So it is a very interesting place. Moffat. Wait. A long time ago, actually, in 1984, he used a well-known random system of equations from gas dynamics because he was interested in boundary of the volume. It's called boundary value problems. And he used some modification of that to the situation and wrote the equation, the following equation for function of psi, which is the stream function of psi, because that is an equation of continuity, that's why hence this function this. And this is the equation, which is the second order nonlinear partial differential, or third order partial differential equation with constant mu because of viscosity. And then the boundary conditions come from the real problem. So altogether, the problem was to solve that equation, to investigate that equation using the conditions, boundary conditions 17. So they are not initial conditions; they are some kind of boundary conditions. And then he suggested to look for the solution in the form of semi-similar, by the similarity approach, and came to the solution in certain form, namely in this form. But in his paper, just it was typographically in such a form, it was confusing. And after that, I saw the paper, first of all, not his paper, but somebody wrote the paper, mathematical investigation of existence of solution, because then mathematicians come, they start talking about the existence of solutions of the problem for the ordinary differential equation, which appeared, but it's not written here. I will show you that equation. Let me just show it to you. The equation becomes like that. So, when I saw the paper, which was published, say, about 3 years ago maybe, it was written like that. With no symmetry, of course, there, it was not symmetry analysis. Just by chance, they tried to find solution in that form. But here the transformation had something like, I don't remember, but it was wrong here, -1 over 2, something like that. Won't change there, and that's why it gave the mistake. So he takes that solution in this form,